This question tests your understanding of how the Ledwall-Wolff shrinkage method affects a covariance matrix. We're using the scikit-learn library's _shrunk_covariance function. Think of it like this. We have a noisy financial dataset and we are trying to estimate its covariance matrix more accurately. I'm going to focus on the key concept of positive definiteness. A positive definite matrix is a special type of symmetric matrix. All its eigenvalues, which are numbers that describe the matrix's behavior, are positive. This is crucial because it ensures that the covariance matrix is mathematically well-behaved and suitable for many statistical calculations, especially those involving multivariate normal distributions. The Ledwall-Wolff method guarantees this positive definiteness, something a standard sample covariance matrix may not always do, especially with high-dimensional data. The shrinkage parameter, often called delta, controls how much shrinkage occurs. A value of 0 means no shrinkage at all, you're just using the sample covariance. A value of 1 means complete shrinkage, you're using the simplified target matrix. The Ledwall-Wolff method cleverly calculates the best delta between 0 and 1, ensuring optimal results. It's like finding the perfect balance. I'll explain this in simple terms. Imagine the sample covariance matrix as a noisy picture of your data's relationships. Shrinkage acts like a noise reduction filter. By combining it with a simpler target matrix, it reduces the variability and uncertainty in the estimates, leading to a more stable and reliable covariance matrix. It's more accurate. The determinant of a matrix is a single number related to its size and scaling properties. While shrinkage often alters the determinant, it doesn't guarantee an increase. The primary goal is to create a more stable and reliable estimate, not necessarily a larger determinant. It depends on the data and the calculated shrinkage intensity. I'll explain the Ledwall-Wolff method. It's a clever technique that automatically finds the perfect balance between the sample covariance matrix, calculated directly from your data, and a simpler, more stable target matrix, often a scaled identity matrix. Think of it like this. The sample covariance can be noisy, like a blurry photo. Ledwall-Wolff acts like a sophisticated filter, sharpening the image by mixing the blurry photo with a clearer, but less detailed one. The result is a covariance matrix that's more reliable and less likely to give you misleading results. This question tests your understanding of the Ledwall-Wolff shrinkage method in scikit-learn's _shrunk_covariance function. We're checking if you understand how it impacts the covariance matrix. We need to carefully consider each statement's accuracy. This statement is absolutely true. The magic of Ledwall-Wolff is that it always produces a positive definite covariance matrix. This is super important because it means the matrix is well behaved in various statistical calculations. A positive definite matrix ensures that the results are valid and meaningful. This one is also correct. The shrinkage parameter, which I'll call delta, is a number between 0 and 1. A delta of 0 means no shrinkage at all, you're just using the sample covariance. A delta of 1 means complete shrinkage, you're relying entirely on the target matrix. Ledwall-Wolff smartly picks a delta value in between, finding the sweet spot for optimal reliability. True, that's the main goal of shrinkage. The sample covariance can be highly variable, especially with high-dimensional data. Ledwall-Wolff helps reduce this variability, giving you a more stable and trustworthy estimate of the covariance. This statement is false. While shrinkage can change the determinant, there is no guarantee it will always increase it. The method's focus is stability and positive definiteness, not maximizing the determinant. I analyze the covariance matrix using a technique called shrinkage. It's like taking a blurry photo and sharpening it. The goal is a better, more reliable picture of how the data is related. I use a specific type of shrinkage method. It's named after Ledwall and Wolff and automatically finds the best way to sharpen the photo, covariance matrix. This is my improved, sharper picture, covariance matrix, after applying the Ledwall-Wolff shrinkage. It's more reliable because I've reduced the noise. The shrinkage parameter controls how much sharpening happens. A value of 0 means no sharpening. I just use the original blurry photo. A value of 1 means maximum sharpening. I use a completely sharpened, but potentially unrealistic, picture. The Ledwall-Wolff method always picks a value between these two extremes. The main benefit is reducing the fuzziness. I improve reliability by reducing variability and making the covariance matrix more stable. This is what shrinkage accomplishes. The result is mathematically guaranteed to be well-behaved. This is crucial for many statistical calculations, ensuring I can proceed with analysis without mathematical errors. I'm analyzing a specific covariance estimation technique called the Ledwall-Wolff method. It's used to improve the reliability of covariance matrices, especially when dealing with lots of variables or limited data. Think of it as a way to make your covariance matrix estimations more robust and less susceptible to noisy data. I'm dealing with a situation common in finance. I have a lot of variables and I suspect my simple covariance matrix calculation isn't very accurate. That's why I'm using the Ledwall-Wolff method in scikit-learn's _shrunk_covariance function to get a better estimate. It's a great tool for improving the reliability of my analysis. The Ledwall-Wolff method ensures that the resulting covariance matrix will always be positive definite. This is important because a positive definite matrix is a mathematical requirement for many statistical processes. The Ledwall-Wolff method uses a shrinkage parameter. Let's call it delta. It's a number between 0 and 1, inclusive. A delta of 0 means no adjustments to the sample covariance, while a delta of 1 means we are entirely using the simplified target matrix. So, it's like a sliding scale to find the best balance. The main goal of the Ledwall-Wolff shrinkage method is to reduce the variance of the covariance matrix estimate. Think of this as reducing the noise and instability of the initial estimate, to make the final results more reliable and less susceptible to random fluctuations in the data. This question tests your knowledge of the Ledwall-Wolff shrinkage method for improving covariance matrix estimates. I'm assessing your understanding of its effects, not your ability to perform calculations. We'll analyze each statement to see if it accurately reflects the method's properties. This statement is true. The Ledwall-Wolff method cleverly ensures that the resulting covariance matrix is positive definite. This is a crucial property because it avoids issues that can arise with the sample covariance matrix, especially in high-dimensional data. A positive definite matrix means all its eigenvalues are positive, a mathematically critical characteristic for many statistical analyses. This is also true. The shrinkage parameter, often represented as delta, controls how much shrinkage is applied. A value of 0 means no shrinkage, we stick with the sample covariance matrix. A value of 1 means complete shrinkage, we use the target matrix instead. The Ledwall-Wolff method automatically calculates this optimal parameter somewhere between these two extremes. This is definitely true. The core purpose of shrinkage is to reduce the noise or variance in the covariance matrix estimate. The sample covariance matrix can be noisy, particularly when the data dimension is high relative to the sample size. Shrinkage makes it more stable and reliable. This section's title, Shrunkcovariance Analysis, clearly indicates that we're going to explore a method called shrunkcovariance. This technique improves the reliability of covariance matrices, which describe how variables in a dataset change together. Think of it as a way to make sure our measurements of how variables relate aren't too noisy or unreliable. I'm asking you to determine which statements are true about the skitlearn library's _shrunk_covariance function. Skitlearn is a popular Python library for machine learning, and this particular function helps us work with covariance matrices more effectively. Statement A says that _shrunk_covariance always boosts the determinant of the covariance matrix. The determinant is a single number representing the matrix's scaling factor. I found this statement false because the shrinkage method primarily focuses on stability and accuracy. An increased determinant isn't guaranteed. Statement B claims that _shrunk_covariance always creates a positive definite covariance matrix. A positive definite matrix is one where all its eigenvalues, special numbers associated with the matrix, are positive. This is crucial for many statistical calculations, and I found this statement to be true. The Ledwall-Wolff method, which _shrunk_covariance uses, ensures this. Statement C focuses on the shrinkage parameter, a number between 0 and 1, inclusive, that controls how much shrinkage is applied. A value of 0 means no shrinkage, and 1 means complete shrinkage. I agree with this statement as the Ledwall-Wolf method always produces a shrinkage parameter within this range. Statement D states that "shrunk_covariance" lessens the variance, the spread or noise, of the estimated covariance matrix. This is the whole point of the method. By reducing the noise, we get a more reliable estimate of the relationships between variables. This statement is indeed true. This simply labels the options presented in the previous rows. It's just a label and doesn't require further explanation.